You can stop anytime.
Right?
Don't go blind.
Yep, add C.
Yes.
And if you get like, what's it called? That form, like
Right.
infinity over infinity, you got.
Ah! Shall not pass. Why not? Because I'm evil. I shall now turn you to paper. Wow.
What happened?
I don't know. It looks like we've been drawn by like a 7-year-old, guys.
So how do we turn back?
Guys, I think I have an idea, but it's kind of a stretch. So I think that wizard turned us into paper puppets to teach us valuable lessons about three-dimensional rotation calculus.
Nick, that is so stupid. I can't even.
Guys, let's just move on for now. We'll figure this out later.
Follow me. Let's go this way.
Okay.
Come on, guys.
Yeah.
Yay, we're here!
Look, I found a function that we can 3D rotate.
Yay!
Let's do it.
All right.
All right, so let's do this 3D rotation. So we're going to find this area bound by x equals 3, rotated about the x-axis. So we've got our dx right here, like this. And so since this is perpendicular to this, it's going to be a disk washer method. So you start with pi, and you go your bounds 0 to 3, function 2/3 x, quantity squared, dx. I'm going to rewrite it so that we can do the integration better. 4/9 x squared dx. So all I did was just distribute the squared inside. So now we have to take the antiderivative. 4/9 x cubed over 3. Evaluate from 0 to 3. The 0 term is just going to cancel because you got a 0 cubed times all this. So it's just going to be pi times 4/9 of 3 cubed over 3, which eventually turns into 4 pi when you cancel everything out. And that's how you do this problem.
But why'd you rotate it around the x-axis? Why not rotate it around x equals -1?
Oh, that's a good idea, Al. Why don't you show them?
All right. Okay, so for this problem, it's going to be very similar to how we solved the other problem, only instead of using a dx, you can see that we're using a dy. So again, we have the same function, and it's bound in the first quadrant, and x equals 3. But now we're rotating around the x equals -1 line. So if the equation for our line, or our function, is y equals 2/3 of x, that means that we can rewrite this as x equals 3/2 of y. Now, this means that when we're doing our integral, we're going to do pi times, we're going from 0 to 2 because we're doing it in terms of y. So integrating it from 0 to 2. And then we're going to be doing the outer radius, so 3 minus what we're rotating about, which is -1. So -1. This quantity squared minus this, our inner radius, which is 3/2 y, minus -1. That quantity squared dy. So you can see it's very similar to what we had in the last problem, only obviously it's about y, and we're using a dy. So now when we integrate this with our calculator, we get 11.25 pi as our answer. So, and that's how you do that problem.
Hey guys, your hands turn normal for a second?
No? Vamsy, you can't just ask someone if their hands turn normal for a minute.
Well, we're still paper now, so it's not like anything happened.
Right, yeah. I think, just hear me out, that problem wasn't hard enough, and we need to find a harder one, because that was super easy, right?
Yeah.
Oh, I think I see a harder one over here.
Ooh.
Let's go. All right, guys. I think I saw the problem over here behind this tree. There it is.
But guys, let me tackle this one. Ah! So when we're doing two functions, we got to use this new equation. Pi multiplied by the integral of the upper radius squared minus the lower radius squared dx. So when we draw our dx right here, we got to figure out what our upper and lower radiuses are. Since we're rotating about the x-axis here, we can see that our upper radius, when we draw a line to here, is going to be the square root of x minus 1. Same, the lower radius would be the x minus 1 squared. Let's write the equation real quick. Pi multiplied by the integral of the upper square root of x minus 1 squared minus x minus 1 squared. And we got to make sure we square that again, dx. Now we got to find out where our limits of integration are. So if we just graph in our calculator real quick, we can see that the limits are 1 and 2. Let's write that in. 1 and 2. Now to just make it easier on us, let's just put this entire thing into our calculator and just press enter. So here we are. Enter. We can see that the answer is about 0.942. So roughly 0.942.
Let's rotate it around the y-axis instead.
Why not?
Okay, so for this problem, instead of using the disk washer method, we're going to use the hollow shell method. So what we're doing is we're making an infinite number of these hollow shells that are dx thick, rotating by rotating this dx across the y-axis. So to be able to do this problem, we have to know how to find the volume of a cylinder. So what is the volume of a hollow cylinder? Now, the volume of a hollow cylinder would be the circumference of the cylinder multiplied by the height of the cylinder multiplied by the thickness of the cylinder. So in this problem, the circumference is just going to be 2 pi times x, because x is the same is the radius in this scenario. So it says 2 pi x is the circumference. The height is going to be this function, which is the upper, so square root of x minus 1, subtract minus the lower function, which is x minus 1 squared. And then the thickness would just be dx. It's our infinitesimally small thickness. So as you can see over here, we're going from 1 to 2, as we figured in the last problem. We're going from 1 to 2, and we're finding the volume of this hollow shell. So we can clean it up by taking the 2 pi out in front. Wow, so math, much pretty. So now that we have it all cleaned up, we can put it into our calculator and integrate it. Calculators are your friend, and we get 3.037. Mathematical.
Whoa!
Guys, we're normal now.
All right.
Woo!
Wait. The world is still paper.
Oh, watch this, guys. I can fix it.
Oh,
Nice.
Oh.
Wow.
It's all 3D.
Hey, there's that wizard. Let's get him.
Let's go.
Ah!
Leave you.
No, you bad man. Bad wizard. Bad.
Guys, let's go home now. All right.
Don't you